Feed table, raw materials are feed here. Materials are passes through by a conveyor belt to the bladed beaters.
Big blender beating the tufted fibers to separate tufts and try to individualize the fiber to form a uniform fiber web.
Bypass system or airflow channel to the hopper feeder. Hair-race fibers are beating with pin/wire type conveyor belt for getting a better performance for the next process, and then fibers web goes to contact of carded cylinder, doffer and taker in to deliver a uniform web.
Nonwovens are typically manufactured by putting small fibers together in the form of a sheet or web, similar to paper on a paper machine, and then binding them either mechanically, as in the case of felt, by interlocking them with serrated needles such that the interfiber friction results in a stronger fabric, with an adhesive, or thermally, by applying binder, in the form of powder, paste, or polymer melt, and melting the binder onto the web by increasing temperature. Staple nonwovens are made in 4 steps. Fibers are first spun, cut to a few centimeters length, and put into bales. The staple fibers are then blended, opened, in a multi-step process, dispersed on a conveyor belt, and spread in a uniform web by a wet lathe, air lathe, or carding/cross-lapping process.
And then webs are divided into 2 parts. One is ready to go with a wooden conveyor belts to the thermal bonding process. And another is for mechanical bonding, that is needle punching unit to bonds the fiber with one another for making non-woven fabrics. Staple nonwovens are made in 4 steps. Fibers are first spun, cut to a few centimeters length, and put into bales. The staple fibers are then blended, opened, in a multi-step process, dispersed on a conveyor belt, and spread in a uniform web by a wet lathe, air lathe, or carding/cross-lapping process. Wet lathe operations typically use 0.25 to 0.75 in, 0.64 to 1.91 centimeters, long fibers, but sometimes longer if the fiber is stiff or thick. Air lathe processing generally uses 0.5 to 4.0 in, 1.3 to 10.2 centimeters, fibers. Carding operations typically use 1.5 inch, 3.8 centimeters, long fibers. Rayon used to be a common fiber in nonwovens, now greatly replaced by polyethylene terephthalate, PET, and polypropylene. Fiberglass is wet laid into mats for use in roofing and shingles. In this production line, thermal bonding process consists of 3 heating chamber to generate heat that is for bonding the fiber with one another. Single-use fabrics. Staple nonwovens are bonded either thermally or by using resin. Bonding can be throughout the web by resin saturation or overall thermal bonding, or in a distinct pattern via resin printing or thermal spot bonding. Conforming with staple fibers usually refers to a combination with melt blowing, often used in high-end textile insulations. Hydroentanglement is a bonding process for wet or dry fibrous webs made by either carding, air laying or wet laying, the resulting bonded fabric being a nonwoven. It uses fine, high-pressure jets of water which penetrate the web, hit the conveyor belt, or wire as in papermaking conveyor, and bounce back, causing the fibers to entangle. Hydroentanglement is sometimes known as spun lacing, this term arising because the early nonwovens were entangled on conveyors with a patterned weave which gave the nonwovens a lacy appearance. It can also be regarded as a two-dimensional equivalent of spinning fibers into yarns prior to weaving. The water pressure has a direct bearing on the GSM and strength of the web, and very high pressures not only entangle but can also split fibers into micro and nano fibers, which give the resulting hydroentangled nonwoven a leather-like or even silky texture. This type of nonwoven can be as strong and tough as woven fabrics made from the same fibers. This results in a fabric that is made of fibers held in place through these methods. Nonwoven fabrics can be made from various types of fibers, such as natural fibers like cotton or synthetic fibers like polyester. This allows for a wide range of applications and uses. Strength and durability. Nonwoven fabrics can be engineered to have specific strength and durability properties, making them suitable for various applications where strength is important. Absorbency. Depending on the fibers used and the manufacturing process, nonwoven fabrics can exhibit different levels of absorbency. This makes them useful for products like wipes, medical dressings, and more. Breathability. Nonwoven fabrics can be designed to be breathable, which makes them suitable for products like disposable diapers and medical garments,